Radiation. It's a word that, we all know, we hear it all the time, and it usually comes with this sense of mystery, maybe even a little bit of fear. But what is it, really? Where does it come from, and what does it actually do to us? Well, today, we're going to dive in and demystify the whole thing.
Okay, so I want to kick things off with a question for you, and just think about it for a second. Right at this very moment, wherever you are you being exposed to radiation?
Well, the answer is yes. A simple yes. You absolutely are. We all are all the time. But hold on, don't panic. It's actually a fundamental part of the universe we live in. So let's break down exactly what that means.
All right, so here's our game plan. First, we're going to look at radiation's cellular attack. Then we'll meet the main players in the radiation lineup. After that, we'll figure out your daily dose, learn how we go about measuring the invisible, and finally, we'll get practical with living with radiation.
So, let's start with part 1, radiation's cellular attack. See, the real danger from certain kinds of radiation isn't about getting zapped or heated up. It's way, way sneakier than that. It acts like an invisible saboteur, getting inside our bodies and messing with our very building blocks on a molecular level.
Okay, so radiation basically comes in 2 flavors. You've got your non-ionizing radiation, think light or microwaves, which pretty much just warms molecules up. But then you have the heavy hitter, ionizing radiation. This is the stuff we're focusing on. It's got so much energy it can literally just knock an electron right out of one of your molecules, breaking the chemical bonds that hold you together.
And here's how it usually happens, which is pretty wild. Our bodies are mostly water, right? So radiation doesn't even need to hit your DNA directly. Instead, it can just smash into a water molecule. This creates something called a hydroxyl radical, which is super unstable and highly reactive. It's like a tiny destructive pinball that bounces around inside your cells, damaging anything it bumps into, including your DNA.
All right, so we know how it does the damage, but what's actually doing it? It's time to meet the main culprits. Let's get to part 2, the radiation lineup.
First up, you've got alpha particles. Think of these guys as the big, slow-moving brutes of the radiation world. They're so large and heavy they can be stopped by a single sheet of paper, or even just the dead outer layer of your skin. So outside the body, not a big deal. But if you were to inhale or swallow something that emits them, that's a whole different story. Then you have the beta particles. If alphas are the heavyweights, these are more like the speedy middleweights. They're much smaller, much faster, and they can penetrate more deeply. A beta particle can go right through your hand, but you could stop it with a thin sheet of aluminum foil.
And rounding out our lineup, we have gamma rays. These aren't even particles, they're pure energy waves, kind of like X-rays. And when it comes to penetration, they are the undisputed champs. They can sail right through your body, through walls, even through several feet of concrete. To stop them, you need something really dense, like a thick slab of lead. Okay, now this is super, super important, so lean in for this. Penetrating power and damaging power are not the same thing. In fact, they're often opposites. So, as you see here, that big, slow alpha particle that can't even get through your skin, if it gets inside you, it does about 20 times more damage than a gamma ray that's just passing through. It's all about location, location, location. Okay, so we've got our lineup of particles and rays. But where do you actually run into this stuff in your everyday life? That brings us to part 3, your daily dose. All right, take a look at this. It really puts things into perspective. The average person in the US gets a dose of about 620 milligram a year. And would you look at that big bar on the left? The vast, vast majority of our exposure comes from totally natural sources. Stuff from space, from the rocks under our feet, even from the food we eat. Medical procedures are the next biggest chunk, and everything else is just a tiny sliver.
So what's the #1 source on that natural background list? For most of us, it's this stuff, radon. It's a gas that's totally natural, created when uranium in the soil and rocks decays. The tricky part is it's colorless, it's odorless, and because it's a gas, it can seep right out of the ground and into our homes, where it can build up, especially in basements. And that's not a small thing. We're talking about a huge number here. Over 20,000 deaths in the US every single year are attributed to radon exposure. Let me say that again. It's the #1 cause of lung cancer for people who don't smoke. It's a major, often silent part of our daily dose. Okay, so this all begs a pretty big question, right? If this stuff is invisible and odorless, how on earth do we measure it? Well, that's what Section 4 is all about, measuring the invisible. Let's learn the lingo. Look, the terminology can get a little wild, but it really boils down to asking 3 simple questions. First, how much radiation is a source putting out? That's its activity.
Second, how much of that energy actually gets deposited into something, like your body? That's the absorbed dose. And third, the most important one, how much biological damage is that energy actually causing?
And each of those questions has its own special units, as you can see here. But honestly, the one you really want to pay attention to for your own health is that one at the very bottom, for biological dose, the sievert or the rem. That's the one that tells you the real story, because it takes into account the different damaging power of alpha, beta, and gamma radiation that we talked about. Okay, so we know what it is, where it comes from, and how to measure it. Now for the big finale. What can we actually do about it? Let's talk about living with radiation.
The good news is, the basic rules of radiation safety are super simple. Seriously, it just comes down to 3 things: time, distance, and shielding. Spend less time near a source, get more distance between you and the source, and if you have to be near it, put some kind of shielding in between you. Simple as that.
And this is a really key mindset to have. The goal here isn't to get your exposure down to 0. It's impossible. You can't do it. We're bathed in it every second of every day. The goal is just to understand it, respect it, and avoid any large, unnecessary doses. It's about smart management, not total avoidance.
So why do we care about managing our dose? Because radiation doesn't affect all our cells equally. It loves to target cells that are dividing and reproducing quickly. Things like our bone marrow, the lining of our stomach, and our hair follicles. Which, by the way, explains everything about the side effects of cancer radiation therapy, right? Nausea, hair loss, it's all because those fast-growing cells are being targeted.
And this table really drives home why dose matters so much. Remember, that average yearly dose for a person is less than 1 rem. Now look at these numbers. These are for a single, huge dose all at once. At just 50 rem, you're looking at nausea, get up to 400 rem, and we're talking about a dose that could be lethal. It really shows how important it is to keep our exposure as low as reasonably achievable.
So, we've come full circle. Radiation isn't good or evil. It's not some kind of monster. It's just a fundamental force of our universe, a force that powers stars, enables life-saving medical scans, and at the same time poses real risks we have to manage. Which leaves us with one final big question to think about. How can we best harness its incredible power while always respecting its risks?